Today we're going to be learning about tree diagrams and about conditional probability. But before we get into that, let's take a deep breath and make sure we're ready to learn some new math. So I want to be very clear. Venn diagrams are really helpful in relating the probability of the intersection of the union, but they don't really help us to directly find either of those probabilities. So like Venn diagrams and this formula, really important. They're not going anywhere. It's not like I'm replacing them with tree diagrams, but we do need to learn about another type of diagram, and that is tree diagrams. Sort of the four things that we're going to do in the lesson today is one, we're going to cover a bit of new vocabulary. I've already mentioned conditional probability. We're going to talk about a new notation that we're going to need to know about. We're going to learn a formula that connects those things, and then we're going to do some examples using tree diagrams with this conditional probability. So let's go ahead and get started. So first we're going to start by talking about some vocabulary and notation. And I really believe, especially in a subject like probability that's already really heavily applied, it's important that we have a sense of what our need for that vocabulary is. Like, why do we need this vocabulary? And so to help us understand that, I want us to think about these two questions. So for the first one, imagine that you're sitting at home eating lunch in San Diego in June. What's the probability that you're going to see lightning today? And you don't need to go on some meteorology website to find this out. The idea here is that this is going to be a low probability. We don't have a whole lot of lightning happening in June in San Diego. Okay. Now, I want to ask a similar question. Imagine that you're sitting at home eating lunch in San Diego in June. Now, if you just heard thunder, what's the probability that you'll see lightning today? Hope you guys have an appreciation fact that this is now a high probability. What's interesting is that these are both about the probability of seeing lightning, right? And so I want us to understand that sometimes probabilities are linked to one another. If we have more information, if I now know that I heard thunder, it's going to change the probability that I see lightning. And so that's going to lead into this idea of conditional probability, the idea that probabilities sort of connect to one another and are sometimes related to one another. So the first new vocabulary term that we're going to pick up today is called dependent events. Okay? Dependent events are effectively two events where the probability of one of them depends on the other one. So in this little mini example we talked about here, if one of the events is seeing lightning and the other event is hearing thunder, those are definitely dependent events. So now that we have some new vocabulary, we can think about notation. Okay, so first I want to cover notation you guys already know. You have already seen this notation, P of A. Okay, it's not new. It might be called the total probability of A. And this notation just gives us the probability that A occurs. It's regardless of B. So even if it's connected to B, if I just write this, it means I don't really care about B. I just want to know what the probability of A happening is. Okay, so this is our new notation. Okay, now when I say new, it doesn't mean it replaces the probability of A. This is just a new, different notation. We're going to call for it in different times. First, how do we read it? This thing is read the probability of A given B. Okay, and what it does is it gives us the probability of A given that we know that B occurred. So this is sort of in fact, this is called a conditional probability. Now, just to be clear, these are both ultimately probabilities of A. They're both about A. The difference is that this one is just saying this is the probability of A. We really don't care whether or not B has happened. And this one, the probability of A given B, is the probability of A occurring given that we know that B has already happened. In this next slide, I want to take an opportunity to sort of practice using this new notation and make sure that we understand what they mean before we get into using tree diagrams with this. So I want to think about a quick example, right? Let's think about a fair 10-sided die being rolled, and let's define two events. Let's call E the event that it's an even number, and R be the event that it's a prime number. I didn't want to use P because the P is already for probability, and it might have gotten confusing. So R is going to be for a prime number. So I want to think about these probabilities. So first, what's P of E? Okay, well, first, what it means is it's the probability of rolling an even number. Okay, so now we go on to thinking about its value. Well, the value of this thing, if we sort of think about, rolling a 10-sided die, it means we have the numbers 1 through 10, so that means there's 10 possibilities. Okay? Of those 10 possibilities, 5 of them are even, And so we wind up getting that P of E is 5/10, which we could simplify to 1/2. P of R should also be really simple. So go ahead and pause the video, make sure you can do that one on your own. Should be really quick, really easy. So that one, of course, is the probability of rolling a prime number on a 10-sided die. For the value, again, there are 10 total possible values that we could get. And of those 10, only 2, 3, 5, and 7 are prime. So this is 4 out of 10, which means this is a 2/5 probability. Okay. Now these next three get into our new notation, these conditional probabilities. Remember that when I've got something like this where there's that bar in the middle of it, that's called a conditional probability. So I'm going to go and do the first one with you, and then I'll give you guys some space to try the other two on your own. So first of all, what does this thing mean? So think for a moment, what does this thing mean? This should mean the probability of rolling an even number given that what I got was prime. Now let's talk about the probability of this happening, right? How many possibilities are there? Well, given that my roll was prime, there are only 4 possibilities. Of those 4 possibilities, how many of them are even? Well, if we look up here, only the 2 is even. So the probability of getting an even number given that it was prime is 1/4. Okay, so if you think you've got that, go ahead and pause the video, try the next one or two on your own. I'm going to go ahead and go through those ones next. So this next one should be the probability of rolling a prime number given that what I got was even. And now to find that probability, I need to think for a moment, given that my roll was even, well, there are 5 outcomes that are even. Those are 2, 4, 6, 8, and 10. Now, of those 5, how many of them are prime? Well, 2 is the only one that's prime, so this is a 1 in 5 chance. The thing I want you guys to notice here is there is a difference between these two probabilities. When I change the order of these events inside, it changes the relationship, which means that these probabilities might change. They might be the same, they might change, they're not the same thing as one another, and I hope you guys have the sense for that. Let's go ahead and look at this last example now. So this one is now saying, what is the probability that I get a non-even number, so an odd number? So what's the probability of getting an odd number given that what I had was prime? And finding the probability for this is going to follow the same pattern, the same process we used for the other ones. We begin by thinking about the condition. Given that the roll was prime, well, there are only 4 numbers out of the 10 that are prime. And I want to know how many of those are odd. Well, 3 of those were odd. So we have a 3 in 4 chance of that happening. So this is sort of what it looks like to use this notation and to think about conditional probability. We're now going to go into thinking about how we can use that in a formula and then in a tree diagram. So there is a formula that's really helpful that sort of governs conditional probability and intersections, and here's this formula. The formula states that the probability of A and B both happening is equal to the probability that A happens times the probability that B happens given that A happened. And so ultimately what this formula is saying is it's saying that if you want the probability of both A and B happening, you need to multiply the probability of A by the probability of B. But remember that B may be dependent on A happening. Okay, we're going to use this formula a lot when we're constructing tree diagrams. There's one more thing I want to say about it, and I don't want to take a lot of time on this, but I do want to point out there's another way to rewrite this formula. I could actually divide the A over. I could get the probability of B given A to be equal to the probability of A intersect B divided by the probability of A. And I guess I kind of wanted to point out, we inadvertently did this on the previous slide. Like when we did, for instance, the probability of even given prime. I don't know if you guys noticed, but what we did was we started off by saying, well, when is it prime? When is this thing prime? And we said, well, there are 4 prime numbers out of 10 on that 10-sided die. Then in the numerator, we said, of those prime numbers, how many of them are even, right? And we noted that there was only 1 even one there. Really what we're doing is we're looking at what's the probability of being even and prime, and there was only 1 out of 10 of those. Then you can see that these 10s kind of drop out in the denominator and we're left with that 1/4. This formula we were sort of inadvertently using on the previous slide, we're going to come back to this idea a lot later. I just wanted to mention it here for those of you that want to see a little bit more of what's going on. If that section I just talked about there doesn't make a ton of sense, that's okay. For what we're doing today, this formula is really going to be important for what we're doing with tree diagrams. All right, so we're finally getting to tree diagrams. Okay, so here's this example. I'm just going to dive right into an example and help you make sense of tree diagrams through that. So it says, if a student studies, there's a 90% chance they will pass their math test. But if they do not study, there's only a 40% chance of them passing their math test. The student studies for 80% of tests. What's the proportion of tests that the student passes? So something that's important to do first is sort of to define the two major events of what are happening here. Okay, one of the events here is the event S, which is that the student studies. Okay, now some of you might think that there are two other events, pass and not pass, but ultimately that's really just one event. It's the event P, which is to pass. If you want to talk about them not passing, we could just call that P prime, right? Remember, we've got that notation P prime, which would mean that they fail. So I don't really need a third event here. These are the two events that we have. Okay, and when you build a tree diagram, what you're doing is you're basically making a little tree. And coming off of this tree, we're going to look at what the next possibilities are. So the first challenge in tree diagrams is figuring out what event do we put first. Should I put the study event here and the passing event here, or should I put passing here and studying here? And really what it all comes down to is you have to put the unconditional event first. So in this problem, which is the conditional event? Okay. Which is the event that depends on the other event? In this example, it's the pass event that is conditional on the studying event. And so that means we want to put studying and not studying over here, and passing is going to be our next branch. Okay? Now the problem says that the student studies for 80% of tests. So on this S branch, I'm going to put 0.8. And that means that, so if there's an 80% chance of them studying, what's the probability that they're not going to study? Well, that has to add up to 1, so this would be 0.2. Okay? Now, in this next branch right here, I'm going to be looking at passing and not passing. Again, passing and not passing. Now I want to go through and I want to fill in these branches, right? So this branch right here is really not just passing, it's actually passing given that they studied. And so if we look back at the problem, it says if a student studies, given that they studied, there's a 90% chance they're going to pass. Great, I'm going to put 0.9 up here, and that means I'm going to put 0.1 here. Because if they have a 90% chance of passing, they're going to have a 10% chance of not passing. So what am I going to put in these two branches down here? Right? Well, this right here is the probability of passing given that they don't study. So again, if we look back at the problem, it says that there's only a 40% chance if they do not study. So this branch is going to be 0.4, and this branch down here is going to be 0.6. At this point, we've set up our tree diagram. What I want to do now is I want to sort of fill out for each branch of this, what is the probability of that branch happening? And this is where we use the previous formula, okay? What I'm doing now is I'm going to multiply this branch times this branch. My previous formula told me if I want the probability of studying and passing, I should multiply the probability of studying with the probability of passing given that I studied. So this top branch is 0.72. That's just me multiplying these two things. The next branch down is 0.08. This next branch down is also 0.08. And the final branch down here is 0.12. Okay. Now something you'll notice is that all of these probabilities add up to 1. And that makes sense because like all of these probabilities are supposed to add up to 1. Now let's answer the question. Now that we've finished this tree diagram, what proportion of tests does the student pass? Well, in this diagram, in this fully sort of lined out space, where do I have the student passing? Well, they're passing here and they're passing here. So if I add those two things together, I'm going to wind up with 80%. Okay? Now, it's just coincidental that that matches with this 80% here, that just sort of like randomly happened here. It's not always going to work out that way, but it is what turned out this time. One of the strengths about using tree diagrams is that they can also handle more than two events. You can kind of do that with Venn diagrams, but it can get really messy. This is an example where I've got one event that has three possibilities in it. So my example says a student regularly does one of three things for breakfast and is sometimes still hungry after breakfast. They're still hungry 20% of the time when they eat cereal, 5% of the time when they eat eggs, and 90% of the time when they skip their breakfast. Okay. If the student eats cereal 3/5 of the time, eggs 3/10 of the time, and skips breakfast 1/10 of the time, what's the probability that the student is not hungry after their breakfast decision? So again, the first thing we need to figure out here is which event is the unconditional event? Which event is the event that whose probability seems to not depend on the others for the probabilities that I have here? Okay, and maybe what we need to figure out before then is what even are our events, right? So first, there's the hungry and not hungry event. And then there's the breakfast choice event, right? There's cereal and eggs and skipping breakfast. So which of these is the unconditional event? Which of them does not seem to depend on the others? Well, for the probabilities that we have here, it seems like it's this one, right? The hunger probabilities changed for each of the different things. So when I build this tree diagram, I'm going to have three branches at first because I have cereal and I have eggs and I have skipping breakfast. And then off of each of these, I'm going to be branching out with hungry and not hungry, hungry and not hungry, hungry and not hungry. Now, I'd like to invite you guys to fill out the probabilities in this chart that you feel comfortable with and sort of, pause the video and unpause it so that you can check as we're going through it. So the probability of them eating cereal is 3/5. The probability of them having eggs is 3/10. And the probability of them skipping breakfast is 1/10. I just kind of realized this top probability is 3/5. It might be nice if I change this into 6/10, just so that I can sort of see all of these as really similar things. It might make the adding at the end easier. If you did it as 3/5, that's fine. We'll work it out. Now that I've got those, I'm going to go in and fill in these hunger probabilities. And these are going to change because they're conditional on what happened before. So for cereal, they're still hungry 20% of the time. So that's 0.2. And that means that this is going to be 0.8. For eggs, this was 0.05, and that means this is 0.95. And for skipping, let's say I think that this was 90%, and this was 10%. So those are the numbers that you should have had on these things. The next step now is for us to multiply all of these things out. It seems like it's probably going to make sense for us to go back and think about these things as decimals. So I would encourage you guys to go back and think about these things as decimals. Now what you're going to do is you're going to multiply all of them here and then think about the question being asked. So I'm going to go ahead and pause the video and fill in all of these numbers, and then we'll talk about what to do with them. All right, so hopefully it's clear to you guys where I got these from. I'm sort of following the formula we got a little while ago. I'm multiplying these two probabilities together to find the probability that that full branch occurs. Now that I have this tree diagram completed, I can go back and answer the question. The question asked, find the probability that the student is not hungry after their breakfast decision. So not hungry. So in this tree diagram, where do I see that the student wound up not being hungry? Well, they are not hungry here, they are not hungry here, and they are not hungry here. Okay? So I need to take these three things and I need to add these probabilities together. Right? So if I add these three things together, what I wind up with is 0.775. So there's, 77.5% chance that the student is not hungry after whatever it was that they chose to have for breakfast. All right, so I've got one last example for us here. In this one, I'm not doing it as a word problem. I'm just doing it with sort of like notation. So I would encourage you guys to think on this problem. What are the two events? Which is the unconditional event, which means which one should you branch first? And then I want you to build the tree diagram and notice, like, I don't even really want to talk about these things yet. Let's build the tree diagram first, and then let's figure out how to answer those questions. So pause the video, try this on your own, check back in and work through it. So from the information that's given, it's pretty clear that D is the conditional event. D is the one that matters whether or not C happens. So that means I should be doing C first. So I'm going to put C here and not C here. And then off of this, I'll branch D and not D, D and not D. Okay. Now I can go back and I can fill these probabilities in. Okay. We were told that the probability of C happening was 1/5. That means C not happening is 4/5 because of the law of the excluded middle. Now when we move on to the next branch, we get to our conditional probabilities. The probability of D happening given that C happened is 2/3. So that means this is 2/3. So this other branch is 1/3. The probability of D not happening given that C did not happen. So this time they gave me the bottom branch of this one, and that's fine. I just have to notice that this is the bottom branch and not the top branch, and that means that this one has to be 5/6. Okay. Now that I have these things, I can multiply out each of these things. Okay, so along the very top, I'm going to have 2/15. In this branch here, I wind up with 1/15. On this branch, I have, 20/30. And along this very, very bottom branch, I wind up with 4/30. Now, it's definitely worth noting, I'm going to want to add these things together at some point, so getting a common denominator across all of them is really valuable. You might be inclined to sort of simplify. I suppose we could simplify all these down to 15ths, right? So if I reduce this one down to 15ths, it would be 10/15, and this one would be 2/15. You guys might have noticed that this one here could be simplified down further. Could have made this one 2/3, but I don't really want to. I want them to all have a common denominator so I can add them. Now that I've got these, we come back and we answer our question. Okay. Question A asked, let's see, and I'm going to do these with different colors. I'll do A in blue. So question A asks, what's the probability of C and not D happening? Well, if you look at all of this space right here, where does it happen that both C happens and D does not happen? The only place where I have both C and not D happening is right here. So the answer to part A in this question is 1/15. Okay, now I'll use green for this other one. The probability of not C happening or D happening, and we kind of have to look at this, right? Not C happened here and here. Because remember, this was like the whole branch for not C. And then D happened here and here. Okay? Now, I'm interested in an OR probability. I want to union those things. Where does it happen that one or the other or both of them happen? Well, it happens at all three of those. Okay? So this is going to wind up being 14/15. And that's my answer for part B. Okay, so I really, really love building a tree diagram, finishing the whole thing out, and then at the end of the whole thing, answering whatever question has been asked. So I hope that all made sense. I really love tree diagrams. They're really, really powerful tools, and I hope they make sense to you guys.